Usually, what do we do in a discussion about a topic, right? We talk about how we code, is it the correct way or not? But in this workshop, we'll look at why this technology exists, what happened before, why now, and all the internal details of the Java design. Okay. So a new technology usually when it gets dropped, right? Like around early 2010s when microservice architecture, for example. So we were all happily coding monolith. We also had a similar session before, right? So we were all happily coding monolith. Suddenly Netflix drops few open source softwares, right? You have Zool, you have Histrix, you have Zookeeper, everything was dropped. And now Netflix, which is a successful organization, shifted to microservice. And then Amazon also followed suit. Now they were all claiming that the entire page of Amazon is now all powered by microservices architecture. So two massively successful companies are saying this is the future. Then what happens to the rest of the software world? We just follow suit, jump into the bandwagon, correct? And there is master class everywhere about microservice architecture. Suddenly, a year ago, Amazon comes back and says, okay, Prime Video, right? We are not using microservices anymore because it's very bad for our use case. And then again, they shifted to monolith. Now you could see talks everywhere about monolith again. So where does the actual truth lie? Like many problems, the answer is it depends, right? So we have to understand the fundamentals, why we are in this position always, correct? So the same thing is happening for the virtual threads also. So the moment you hear the term, we all go hungo, right? So we are saying, oh, virtual threads is going to be very fast. I wrote a very bad application, but suddenly it is going to run very fast, correct? No, that is not going to be the case. We will see why. Of course, it is a better feature. Your application is going to become more performant and everything. But we have to understand why. It is not suddenly people became intelligent and came up with this feature, correct? All these things have been existing earlier also. The hardware is not changing, your OS is not changing. But what changed in Java that is enabling this highly performant application, right? Okay. Right. So for this talk, these are the rules. Okay. Whatever information that I am telling, it's public. Although I work for Oracle JDK, there is no information that is private only to me. Okay. Everything is in Open JDK. You can see the code, and you could have you could listen to similar talks and articles in these sites, dev.java, inside.java, etc. And if you want to really understand because the development is still going on for the project Loom. So there are so many areas to cover, especially the serviceability area where debugging and profiling is involved. So the development is still going. If you are interested in this and you want to go deep dive into this world, you could always go to this site, jdkjava.net and Loom. You could subscribe for the mailing list. You will know what is happening right now. Okay. So I'm going to dwell you in the fundamentals. Okay. So if you have any doubts, please ask. No question is so stupid. Don't think the other guy will know and he will judge me. There's no judgment here. Ask any question at any point of time. But if you are unhinged in asking question, of course you will face two scenarios. You could be asking some question that I have answers in coming slide. So I will tell so if that happens. The other thing also, you could ask some utmost irrelevant question also. That is also possible. I'll also point out if that is happening. Okay. So first thing is you have to be ready with JDK 21. I hope everyone has JDK 21 in their systems, right? Okay. Right. And you could download the source code from that site. Okay. GitHub. It's public. Anyone facing problem cloning that? We are good. Only few Java files are there. So nothing fancy. There's no pom.xml, no dependency. It's all core Java. You just have to compile and run. Of course, there is, I think from JDK 11, you could just run the source code as it is. No, but yeah, but still we will do the old fashioned way. We'll do the Java C and then Java. Okay. Right. Okay. Yeah. Yeah, the last one. Sorry. This one. Is it? Mm, this. Okay. Yeah, this is the one. All good? Okay. Get back to this. Okay. As I said, context is important, right? So let's get back to some history lessons, okay? JDK started with the concept of green threads in terms of concurrency. So Java is one of the very early high-level language that gave you support for threading and synchronization primitives. So when they started, the JDK architects made the threads as user-level threads. So it was not actually a OS thread. Okay, all the threads and task units are maintained by the JVM. Okay, so why did they choose this particular design? Is that it allowed for easy portability. So when JDK was introduced, that was the main buzzword, right? It is portable. You write once, you run everywhere. So for that, so those days, the OS, the behavior of various OS at that point of time in the market was not consistent. Now you have almost every OS that you can trace back to Unix kernel. So those days that was not the case. There were so many RTOS and Java had to support all those things. So it is better not to depend on the support of OS. So the threads were maintained at the user level by the JVM. That was the portability was the advantage. Of course, scheduling also there was a lot of non-uniformity across all the OSs. So with independent scheduling that was done by JVM, it was all the portability was very good, and your application behaved the same across all the OS. So that was the main thing at that point of time. Of course, you could see the problem immediately, right? So even though multi-core processes were not that prevalent at that point of time, this we are talking around 95, 96 time frame, right? Even though that was true, when there was multi-core processor present, JDK was not able to use leverage that support. Again, so this is all one thread, right? All the user level threads are mapped to only one OS thread. So which means that when any task in your Java application is going to do a IO operation, it is going to block. All other threads are not going to run. Okay, so this is how they started. So it was okay that those days it was fine because you weren't writing that powerful applications or highly concurrent applications. It is, see, blocking IO is a side effect. So your main objective at that point of time is the portability. To do the portability, you maintain every thread in the user level mode, right? And you do all this multiplexing. The JVM was doing everything. JVM's runtime was doing everything. The side effect was the blocking IO.
It's more of a round robin scheduling, right? You are thinking two kids, right? So you see this kid 5 minutes, see this kid, but you are one. So this was not an issue because RAM is talking of something like 20 years before. Okay, so it may not make sense for you right now. But 20 years before it was making sense. Yeah?
Okay. So they were using what we call the green threads because JDK was incubated in a project called Green Project. So blocking I was more of a adjustable side effect. So people didn't really, it didn't matter much at that point of time. Right. So what is happening parallelly in your processor world, right? So Moore's law was in full swing. You could see the proliferation of number of transistor counts in your chipset. So as and when we are moving along the timeline, your processor was getting faster and faster. So even the Java application developers were happy because you just have to write code once. Every year your code is going to get faster without you doing any work. Then we know the free lunch is going to get over at some point of time. Even Moore told so. But there was this very nice paper by Herb Stutter where he really showed why this is going to stop. The transistor is not going to multiply forever because you make the transistor smaller and smaller. At some point of time, you are going to have problems with the quantum effect, and you have more and more transistor in a small area. Of course, you will have to deal with the heat dissipation. So all these problems were there. You could see that at some point of time, you are the last pink line, right? That's what we want, the performance per cycle, right? That was tapering after some point of time. Okay, so all these things were happening at the background. So around 2 years later, right, JDK 1.2 was released, and they switched from this green threads to one-to-one mapping with the OS thread. So why did they do? Because they could see that multi-core processors are getting more prevalent day by day. So you cannot sit with mapping all your application thread with one OS thread. So that is one thing. And the other hidden advantage was the code maintenance of JDK was pretty much simple if you map one-to-one. So you don't have to do this. OS thread scheduling is altogether a big concept on its own, correct? And to maintain that in your JDK code, and it's a duplicate of what OS is also doing. OS is also scheduling threads, and in JVM also you're scheduling the same. So all this code were duplicate, and when they did this one-to-one mapping, right, code become very simpler. Okay, so now where are we? Now we are seeing that the transistor count is going to stop. So the industry is moving away from making your cores faster and trying to fit as many cores as possible in one chipset. Okay, that's the transition that is happening. So what does it mean? Your application should move away from trying to think in one thread, and you should shift to more and more concurrent, doing your code concurrently. Okay, so when that is happening, what happens to the memory part, right? Is your processing speed is going higher and higher, but is memory access catching up, right? Around, you could see around 1980s, it was all, the performance was almost same. Okay, so as time progressed, processor performance increased many-fold, but performance gap you could see between memory access and this has varied very much. So what does it mean for any Java developer, right? So when you try to do any calculation or processing, that is going to be very fast. But if you try to access any heap memory, that is going to be slow. Okay, so that's the after effect of what is happening in the processing world. So which means that processor is going to sit idle most of the time. Okay, so you have something called caching.java. I'll just show you the code right now. You could see the code, right? Okay, so the code is pretty much simple. You have an array, okay, a big array, and you have two different methods. So this touch every line is going to access every element of the array, okay, and touch every item, and touch every line is going to skip 32 items, and it's going to touch only every 30-second item. Okay, now if you just look at the code, and we are trying to time touch every line, and we are going to time touch every item also. So which code will run fast, touch every line or touch every item? Every item is going to be slow because it's right. touch every line, it's going to execute fast because it is going to access only the 32nd item of the array, right? And this is going to give you the diff in terms of percentage. I'd like you to run this code in your laptop and see. So how many of you have x64 laptops? Okay. Okay. How many have ARM? Rest all are ARM, right? Okay. So I am going to run this. Right, you could see that there is significant difference between touch every line and every item, right? Line is actually taking lesser time than the item, right? But what about x64 people? Any x64 people running this? Is it still different? It's consistent throughout? Seeing the difference at all? Okay, this is a, sorry? Okay, sometimes actually you should see negative also sometimes. So, okay. So what is happening? So it would have been a bummer if this is the case for everyone. At least few are seeing not much difference, right? So what is happening? Many processors, right? x64 especially, x64 instruction set based processors, what they do, they prefetch, okay? Because we know that accessing main memory is going to take time, okay? So when they're going to fetch data, they're not going to fetch only what you asked for. There's something called caching line size, okay? Typically it will depend on the processor. Some processors will have 128 bytes, some processors will have 32 bytes. So based on your caching line size, right, it will try to prefetch and keep it in the processor's internal cache, right? That's why when we are trying to skip 30-second item, and if you are trying to access all the items, in some laptops it's going to be the same. So why I am trying to showcase this is that your processor is pretty fast. The time difference only happens because of the access. Okay, so that's the lesson we are trying to understand here. Similarly for the network calls, right? Your network calls is going to take a lot of time comparing to what you are actually processing. Okay, right. So yeah, so when all these things were happening, what was happening in the software development side? We all moved from monolith to microservice. Everything is a network call right now, correct? So even when you don't want to do some addition, you go to some service dot some call, right? That's how we have actually transitioned. So everything is networking call. Of course, you do have to have database related calls. So that's a unavoidable scenario. So most of the time, your processor is sitting idle. Okay. Okay, a quick look at how JDK has evolved when all these things are happening. So you could see we started with the green threads, and then we moved to one-to-one mapping with the OS threads around 1.2, and around the JDK 5, right? All the important util classes came into picture. Your Java util concurrent, and then in JDK 8, completable future and streams came into picture, and with 19 virtual thread came into picture as a preview feature, right? In JDK 21 it is actually delivered, it is a permanent feature. Okay, if you are kind of a trivia buff, this is happening every 10 years. So if you are, so 1.0 was 1996, 1.5 was 2004, 1.8 was 2014, and 19 was 2023. So, right. So, which means that we end up with these two kinds of programming style, right? Because of all these things happening in the background, your architectures have moved towards more networking calls, and your processor is faster also. So you have synchronous and asynchronous. So synchronous style of coding, right? It's pretty much the best way for us to code, because it's all imperative style. You just do call 1, 2, 3, done. Okay. So any request, web request comes to your endpoint, you say, okay, create a new thread, finish off, return your data. Okay. So the problem is it doesn't scale well. Okay. You cannot create many threads and handle so many requests at one point of time. Okay. Which means that you have to try to optimize your processor usage by doing asynchronous code. Okay. Asynchronous code, no matter what people are saying, it is really difficult and cumbersome to code. It is even more difficult to debug and do a profiling. So I did a small code for my friend, pro bono basis, right? I reduced the code pretty much very simple using Spring Reactor. The development team rejected because they didn't understand. I can't take this code because you wrote it once, but who will maintain it? Who will debug it, right? So it is good for the use efficiently using the processor time, but it is very bad for the developers. So look at this, compare these two codes, right? The right one, that's the simplest I could try to code. Okay. Whatever I went through many iterations using reactor code or vertex code, nothing I was able to fit in a small time. I used lambda where whatever I do, I could not fit in that small size. And eventually even this code doesn't actually compile. I had to show that asynchronous code looks in some way. That's why I have shown. So it is very difficult to write and debug. So we are left with a very bad trade-off, right? Wherein either your development is easy or your this one hardware you are not able to optimize well. Okay. So I told. Sorry. Yeah. Yeah. What is this asynchronous style of coding, right? You are trying to be non-blocking as much as possible, which means that you have to take care of callbacks very much, and you have to wire everything in a nice pipeline. That's where your difficulty with writing code and debugging comes into picture. But as you said, yeah, performance-wise, asynchronous code is better, right? Sorry. Yeah. Debugging, profiling is difficult, right? Yeah. I mean, you feel good writing, saying, I have written a very complex code, but yeah, maintenance is very right. So yeah, so I keep saying that you have a limitation with the OS thread, right? So let us just see if you have, so everyone run this max thread code, okay? Okay. Okay. So this is a very simple application. Okay. So we are going to see what is the threading limit. Okay. So here you could see I am creating the legacy OS thread, platform threads. Okay. And I'm going to pass that and run as many times. Okay. Simple application. You should also try doing that. So let me start with 2000. So I am able to create 2000 threads here. Okay. So this is what Apple laptop 32 GB. Yeah, Mac. So yeah, 32 GB RAM. So we are testing. So 4,000 threads we are able to do. 8,000, no problem. So the moment you go to 9,000, you hit this out of memory error. Okay. So you see what we are actually doing in the task. We are not doing anything at all. So we are just trying to sleep for 1 second, right? So your process, can you run so many threads doing this in your processor? Of course you can, right? But what is not allowing that? Because you are hitting the memory limit, correct? That is because your JDK from JDK 1.2, the mapping is 1-to-1. For every Java lang thread, it is creating a similar OS thread. Okay. So although you can manage so many threads, you are not able to do so. Right. And of course, the limitation would change depends on your RAM size and all, and your OS too. Okay. Done. Yeah. Quick detour on parallelism versus concurrency concept. Although people keep explaining this concept, we are not able to understand because they are giving real world examples. So that's why we are not getting it. So this entire workshop and talk is about concurrency and not parallelism. Parallelism is a algorithmic problem where you have a single task. Can I improve it better with a parallel algorithm? So you have, say, for example, you have to sum every element of an array, right? The best you could do is order of n because you have to visit every item, correct? But how can you go even further? That is, this particular problem can be parallelized. So you could divide into subarrays and all these tasks can be run parallelly, right? So that is parallelism. And the unit, how do you qualify parallelism? You say, you quantify it with latency. This task took this much time. Concurrency is like you are trying to squeeze as many independent tasks as possible. So one task is okay, it is trying to read a file, another task is trying to access a database, another task is trying to get access a REST endpoint, right? So we have all these independent tasks, but the available processors are the same for all these tasks. So it is trying to compete for that processing resource. That is, how can we manage this better? That is concurrency. So how do you qualify that? Throughput. You say I achieved so many tasks per time. So per millisecond or something, 100 tasks per millisecond or something. Okay, right. Now we are all understanding, right, where we are with a higher processing power, the shift in our software architecture, everything, right? Now the Java architects have a problem. So we are hitting the OS memory limit pretty much, and all your application are just waiting in the IO call, not doing any work, right? So we have to fix this. And of course, Java architects, they cannot just do something on their own, right? It has to be, there has to be a sound theory behind that. So that is called Little's law. It is actually from operational research, where the formula is very simple, right? The concurrency equal to throughput into latency, pretty much straightforward. The amazing thing about this law is that it is true for any probability distribution of your request, right? So it could be normal or it could be binomial. It doesn't matter how the request is coming inside your closed system. This formula is going to be true. Okay. Now, what do you want actually? We want to increase the throughput. So the lambda has to go up, right? Now latency, we cannot touch anything, right? You have to run your task. You cannot say, okay, I want to increase the throughput. So instead of summing up the entire array, let me sum up only half array. You cannot say that, right? So latency is going to be there. What is left in this formula? Concurrency. So the answer to the problem is you have to squeeze in as many threads as possible. So that's the answer, right? So typically, processor usage looks like this, right? So you have the processing done, and most of the time, your I/O, you're blocked in the I/O, and where we want to be, that's in the right side. Your processing time has to be, the processor has to be used the entirety of the time. Okay, so how many of your teams actually have a DevOps kind of guy monitoring your CPU usage in your company? They are doing, right? They are doing it, right? So they will come and say, look, you're not using my compute, cost for my compute is getting wasted. Make your application more performant, right? So that is what we are also trying to do here. Right. So that's why they came up with this project called Loom, wherein, so these are the two major portions of Loom. One, you have the virtual thread, the other one is the structured concurrency. Structured concurrency, we are not going to cover much here, okay, because it's just the API. You could just look at the Java doc and figure out. We would talk more about the virtual thread because that's where the fundamentals are, right? So you could see we have in JDK world, nothing gets introduced as it is. So we have something called Java enhancement process. The ideas would be posted to the public domain. Feedbacks would be garnered, and then only something is actually implemented, right? So these are the jobs. The numbers are given. You could always go and read what was the motivation about on creation of this project Loom. Okay. Right. So, yep.
Is that open source? Do we have access to that?
Yes.
Yeah. Right. So it will look like this.
Java enhancement process. Java enhancement process. Right. So what Ram explained that whenever there is idea, or even Praveen was explaining in the morning, right? The idea will be thrown into the community or into the public. Right. So everyone should understand what is the feature and then the development. Yes. So
just serial number.
number.
Serial number. Not, no. Yeah. So, yeah. So this is how it looks. So the entirety of talk, all the ideas actually is there, but we seldom read all these things. So that's why we are here.
And one of the best documents to read.
Yeah, yes. Because yeah, you are hearing from horse's mouth right here. So yeah. So where were we? Okay. Okay. Now we understood the motivation behind the idea of creating more threads, right? So how do we do? So this was where we started with the green threads. Okay, multiplexing so many user level threads to one single OS, and then we move to one-to-one mapping. We are now the rightmost side, the virtual threads, where we are going to create as many virtual thread units as much as possible, but it cannot run on its own. It has to depend on the OS thread to run. Okay. So what happens is that, so you could see, actually I don't have a animation or something. I will show it manually. So these are the virtual thread tasks. So one important thing to understand is everything what I'm talking is happening under the hood. So when as an application developer, when you create only the creation time, there is a difference, virtual thread or platform thread, but rest of it is all under the hood. Okay. So you have virtual thread tasks here, 1, 2, 3, 4, right? And when something has to run, right, it will come to, so, okay. So it will come here. It will get carried by the OS thread and it will run. Okay. So this is called mounting. Okay. So once your task blocks for some IO operation, either you trying to read a file or you are trying to make a network call. This would be unmounted to a queue, 4-join old queue. Assume it's somewhere there. Okay. Then the other tasks, when they are ready, right? So they will be carried by the remaining platform threads. So this uh, uh, process of mounting and unmounting is what allows you to run so many virtual threads with the given number of platform threads. You have to understand that the number of processors are same, right? We are not going to change that. But how are we multiplexing so much is that we are able to mount and unmount. Okay. So you could see that if your task is not blocking, right, then there's no use at all. You're not going to gain any performance by using virtual threads, right? So say for example, all these threads are just adding numbers, right? So they are all mounted onto this actual platform thread. So it is going to processor time would be taken. It's always full. Nothing gets unmounted. All the remaining virtual threads will just stay as it is, right? But what we want to achieve is here. In server-side application, most of the time you are waiting. So that waiting time, your task is removed from the actual platform thread and kept in a queue. When it is getting unblocked, it will again go here and start executing. Okay. So this is the most important thing. This is how it is implemented. Any doubts in this? Yes, if it is done, it will be unmounted, or if it is waiting for an IO, any blocking call, even thread.sleep is actually it is a blocking, right? You are not going to use the processor time at that point of time. So even that time it will be unmounted. So you are trying to access any IO and you are waiting in a buffer for some data to happen. That's a blocking call. It will be removed, and when the data is available, it will come back. Of course, while it is trying to mount, some platform thread should be free. Okay. Yeah, we will see how it is done. Okay. Just right now, let's all assume some magic is happening where it is able to unmount when a blocking call happens, and then mounting happens when things are ready to be run. Sorry? No. Virtual threads, there is no bound. Of course, you will hit. I mean, I can show you the limits also. You could easily run thousands of virtual threads. Sorry, millions of virtual threads. But you should understand where we are saving. We are saving in the memory side, but processing side, there's nothing. We still have the same number of processors, right? So every thread is doing something. You cannot squeeze in with the existing processors. So the use case is this, where usually in server side applications, right, you are waiting for the IO, you are blocked on the IO operation. Either you are trying to fetch data from database, or you are accessing NFS files, or you are trying to do a REST API call, where you are not doing any job, right? You just made a call and you are waiting for the data to come. That time, what we are doing is we are moving you away from the processor and utilizing someone else and giving them the chance. So the writing style also matters. Yeah. If you talk about use cases, right, there are so many things in the application. Broadly, there are only two. One is IO intensive operations. Other one is CPU intensive operations. So CPU intensive operation is what? You multiply matrix multiplication, you do something with machine learning, or you do encryption kind of things where you do a lot of calculations. So those are CPU intensive tasks. IO bound task is what majority of enterprise applications are doing, right? You do some calls or something, and this is a practical problem that we are facing. It's not a theoretical one, right? So you could see that when you profile your CPU usage, it is not efficiently used. Why? Because most of the time your application is waiting for something. Right. So context switching is a good question, right? So you have millions of virtual threads and you're trying to switch it again and again, right? So what happens to the context switching time? That's the question. So you could see the difference between the virtual thread and platform thread here. So of course, we were talking about the memory usage. Stack size is very less, right? So you have 1 MB for platform thread and pay as you go stack, which means that your virtual thread, your stack is not, you don't assign too much memory in the beginning itself. Okay. So if you have you do a recursion, you have stack depth of say 20, your stack size will be allocated accordingly. You have only 2 calls, it's only 2 call depth. Okay. So that's where we save a lot of memory with the virtual thread. When it comes to switching time also, this is not your actual OS scheduler that is doing. Okay. When OS scheduler is switching, right, it has to do a lot of things because the memory also it has to take care. But here in our virtual thread, the switching time is very, very less. Okay, we'll see what it means to switch also the later. So you could appreciate that the time taken will be very less. Right. Platform thread, correct. Right. That's what the underlying hardware never changed, right? The processor for executing an instruction, you need the processor, correct? That is not going anywhere. So in my laptop, it's 10 cores. 10 cores is going to stay same, correct? But when I am trying to run a task which just was sleeping for 1 second, I could not run it because it was hitting the memory limit, correct? So similar way only we write our enterprise application also. Most of the time it is not doing much. So such application you could squeeze as many as possible with virtual threads because it's just waiting for something to come back.
Mostly like what is the data we have collected? It's like 50% IO and 50% CPU. This is how most of the pods and most of the deployments happen, right? So those are the scenario where you should go with the virtual. It is not like purely computation. I mean, purely computation, either you're creating virtual threads or you're creating normal threads. Right? Everything is just doing the computation, right?
Right.
Every seat have a, and you have to press a button. You should come here. Your picture should come. Is it not? Hello. Okay. Huh? It's coming. It's coming. Some of them are not working. You are the unlucky one.
So question was more of the choice of virtual threads. For what use cases you are trying to do that, right? So you're saying, what if my services is not doing any IO operations, or it is not designed for that kind of workload, correct? Is that your question? See, the migration towards virtual thread, that's what we are trying to establish here. You don't have to migrate and expect your application to suddenly run faster. That is what we are trying to establish. You have to see what your application is trying to do, right? Of course, you have your CPU profiler. You could see if the CPU is getting utilized properly or not. Okay. When you see it is idle for most of the time, you should look at your applications. What is my application doing? Is it sitting idle? That's why it is reflecting that CPU usage is very less. At that time, you start using the virtual thread, which means that you could you start with serving only few requests. You start from there, you have to migrate using virtual thread and start serving more and more requests. Okay, your question is how do I identify whether my application is blocking for any call or not? Is that your question? Okay. 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 What you are saying is, say you have a database. It has a limitation of accepting 100 requests per second or something. Now, earlier you had an application which is having that it is able to utilize that much only, right? Now you are going to use virtual thread and I'm going to hit the database services with so many requests. That's what you should not do that. Actually, there is a slide talking about that rate limiting. Okay. Right. So this concept is clear, right? Mounting and unmounting. Correct. Right. 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 So this thread pool, right? It is usually the number of threads that are created for handling virtual thread is equal to your number of cores in the system. So right now this laptop supports 10. So 10 platform threads would be allocated to handle virtual thread. Yeah, that's what we are trying to do. So again, the idea is not new. It's again user level mode thread only. Just that the entire scheduling is not taken care by the JVM runtime. It is somewhere in the middle. So we are not in one-to-one mapping. We are not into the green threads. We are somewhere in between. Right. It's still only 10, number of cores into that platform threads. Right. Correct. True. That's the power of virtual thread, right? So you are scaling, say, right now in your application, you are doing 1,000 threads and you are going to scale to, say, 1 million virtual thread. That's just the thread perspective, correct? Rest of your application, you create some 3 objects per task that is getting multiplied. So you have to be aware of those consequences.
So I have a question. Does this completely override the Java NIO selector, or do you think Java NIO selector will also have use cases once?
Right. Good question. Right. So how is this all these things happening? So we are saying when your task has a blocking call, I'm going to unmount. So underlying thing is again NIO. So because to support this virtual threads, right, they had a JEP to make every socket implementation into NIO just to support this virtual thread. Because you have to, if everything is blocking, how can I insert my probe saying it is blocking, let me go and unmount? That's not possible, right? So there was a implementation change where right now there is no blocking call at all for the virtual thread. You can use the blocking API from the application side, but underlying it's going to be NIO. Of course, if you want to use the NIO from the application also, I mean, it is not useful, right? I mean,
Yeah. So do you see frameworks like Netty moving to virtual threads already? Or will they continue using
I don't know about Netty, but I have a slide where whatever projects that I cared about, I just collected. They have moved to virtual threads.
Thank you.
Right. JVM. JVM is doing it. Correct. So as I told right now, right, every IO calls were converted to NIO because that's where you get a callback and all, right? So JVM used that feature to implement this. So when there is a data available, the JVM will get a callback. It will understand that, okay, this was supposed to be this virtual threads task. Okay, let me mount him again. Then it will see whether there is any free platform thread available. So most of this coding, right, for implementing this, they try to use the existing feature. So now the scheduler is actually fork join pool scheduler. So they didn't write altogether a new scheduler for. Okay.
Just one question.
Sorry. Excellent question. What about the affinity, right? So we talked about caching earlier, correct? So what was the processor doing? So here the application in the sense OS applications like JVM or any OS application, right? So you don't actually have control of what the processor is actually doing. It can cache on its own. You just have to second guess and try to use this caching mechanism. Okay. Now he talks about affinity. So what is this caching affinity? So when the thread is running, right, we saw that it is trying to fetch data, more data than what you actually want. Okay. The next time, say you say object dot I, it fetched that particular memory from the heap. Now that is actually, it will be stored in the processor cache also. So the next time you actually say object.i, it won't go to the main memory. It will do all these things here, the locally itself. That's where your synchronization problem happens before, and all those things, concepts come into play. So it is doing this. Now his wonderful question about affinity is, now my virtual thread was doing this, correct? After some time it blocked. You unmounted. While mounting, I actually mounted to another thread. So thread, it's actually, unfortunately, it is getting executed in another processor. That might happen, right? So you lose that affinity. Now, there is no problem with the programming construct because caching is always hit and miss, right? So if it is hit, it's good. If it's a miss, it's going to go to the main memory as expected. But you lose out on the caching, correct? So in the fork join pool scheduling system, while scheduling the virtual thread, right, they will try to schedule in the same platform thread as much as possible. If it is free, it is going to the same thread so that we gain as much as possible with the affinity. Right, right. As much as possible, they will try to schedule in the same. Of course, if the platform thread is busy with some other virtual thread, it has to choose.
Basically, we use new architecture. It should use the same thread buffer.
Right? Okay.
We will not take further questions.
Right. You could see the APIs, right? It's almost same. One of the goals of Project Loom is not to introduce too much change. So we have only extra methods to create threads, right? Now we have a new builder method, but otherwise you have a new executor, new virtual thread task per executor. Since virtual thread is cheap, it makes sense to create new virtual thread every time you submit something. Okay, this is the new one.
The older classical thread model is now off.
Right, that's the legacy way of creating thread off platform. The new way is thread dot virtual. Okay, right, right. So I will just switch to the program, right? So earlier we had this platform, correct? Now let us switch to virtual. So let's start with where it failed. 9,000, right? Okay, 9,000 is done. Okay, 100,000 will go. 100,000 is also fine. 1 million also is fine. Okay. You could see we are able to run all these threads because we are not doing much in that run method, right? It's just sleep. So say 10 million. At some point you will hit the memory. It's not like OS is saying it's a virtual thread and it's being kind to virtual thread or anything. So it will hit. Point is you are able to run so much more threads right now compared to the okay, 10 million also it runs. So right. Anyway, you can create threads. Thing is to run those tasks, right? You need your processor. So that's where you'll see the bottleneck. And if it is all waiting for something, you could do that. Okay. So yeah. Right. We were wondering, right, how all these things are happening, right? With virtual thread, you are able to mount and mount the. So this is the main concept behind this. It's a concept from computer science called continuation, wherein you are able to represent the control states of a program uh, in some with some metadata. So that is called continuation. More specifically, we are interested in something called delimited continuation, where we are able to reify this abstract concept into a function. Okay, so this is how it looks. When you do this blocking call, right, you start with thread.sleep, it unmounts, and when it wakes up from the sleep, it is actually getting mounted, right? That is all implemented using continuation. So when thread.sleep happens, right, it goes through the call and somewhere you will see continuation.yield. Okay, while it is waking up, okay, there you will have a code saying, okay, I remember this is the continuation I'm going to run. Since your continuation is actually representing your control state of the program, it can resume from the same place. Okay, so you have something called continuation.java. Okay, for that you have to enable a module because it's all internal. If you see, right, the control continuation. Okay, so it's actually internal. Okay, it's not exposed to application developers. It's just to show what is happening behind the scenes. Okay, so you start here, you say run, your scope will run. Okay, C1 will run, and then you are yielding, right? When you yield, it will come back to your run and it will continue here. Okay, when you call again the run, it will get back to the place where you yielded. Okay, so this is the concept which allows you to do this mounting and unmounting. Okay, so you could run this and see. So you could. So this is the exporting your internal classes, which usually you shouldn't do, but just for demo purpose I'm showing. So this is what we wanted, right? It starts, where is it? sorry, right? You starts, then this code is getting executed. So you could see C1 thread, and then when it yields, it comes back here. So it came back, right? And it again goes back when you say run. It resumes from the place where you yielded. Okay, and again once the task is done, it is going to come back. So this is the concept with which we are able to implement virtual thread. Okay, where are we? Okay. Okay, so again continuation. This is how we do. So you could see the red color thing is the platform thread, and the stack of what you run in the virtual thread is I have represented green color. So you start something like this. There are two platform threads, and you are running your task in the green color is what the stack trace of your application. Okay, so once you hit the continuation dot yield in any scenarios, right, where your IO is going to get blocked, thread dot sleep or database connection, you are making a IO call or some blocking call, continuation dot yield will be get hit, and what you see is all the stack is moved towards the heap. Okay, your application stack is very safe in the heap, and by the time the callback comes and JVM understands that okay, this is the time to wake up my virtual thread, it will again mount the rest of the stack onto the OS thread stack. Now when it is mounting, of course it has to see which platform thread is free. Say at this point of time PT1 was busy and only PT2 was there, so it will mount on that. Okay, so this is what happens behind the scene. Yes, it's more, yeah, it's mostly the stack memory, right? Whatever you do with the thread, it's all in the stack memory, right? So again, correct. Again, this is what you have to keep in mind also. Nothing is free, right? There's no free lunch in the world. You are able to create many virtual threads. These are the side effects. All the stack is going to go into your heap memory, but most of the cases you don't have a very too much depth in your stack, right? Unless of course with libraries and frameworks you might have many, but our application as such you don't go too much depth unless you do some recursion. Yeah. Because this is a very huge change set. If you actually I have somewhere that slide. Yeah, this is the right. So the first line, no, there are so many file changes. You could see the subcomponents. Your compiler is affected. Your GC is affected. Your debugging, all the components are affected. It's a huge change. Okay, and it borrowed a lot of these other changes also. Okay, so this is what happening behind the scene. Your correct. Yeah, correct. Your stack size is less because it will depend on how many calls you are actually making. The green color is small because our stack depth is not much. This is, yeah, typical. So there in that slide, what we said was there is no fixed size. It's pay as you go stack. So if your stack depth is small, what is getting transferred to heap is also small. Okay, right. So so we will test all these theories, right? Your IO and CPU with the code. So everyone move on to this experiment.java. Okay. So yeah, only. Right. So we talked about there are only two types of operations broadly, IO and CPU, right? So I don't have a full-fledged IO operation. What I'm going to do is just sleep for 100 millisecond. Okay. right? So simple application, 30 tasks, all are going to sleep for some time. Okay, so Java, right. Okay, so you could see that. I wrote I mean, I didn't write, but I have a small monitor code here which would show us how long this particular task run and whether it hopped from one platform thread to another or not. You could see that most of the threads actually hopped. So virtual thread 22 hopped from platform thread 2 to 3. So while going to sleep, it was in 2. While waking up, it was in 3. So most of it is hopped. And you could see this is all just coincidence that virtual thread 32 didn't hop. Okay, so you could run this again and again, see different output every time. Okay, so the hopping part is what you have to understand. It need not run in the same platform thread. Okay, so are you guys able to see the same output in your laptop? It's able to hop, right? Okay, so this is more important because we need to understand what should not be done, right? So we were talking about computation intensive tasks, correct? We do a lot of processing. Should I use virtual thread for that or not? So I have similar thing. We are calculating square root for 10 million times or something. Basically a computation intensive task. When this is happening, okay. So when this is happening, right, you could see that there is no hopping going on because your virtual thread never unmounted because it never blocked. All it was doing was calculation, correct? So there's no hop. So virtual thread started with platform thread. It fully completed it task. When these tasks are running, right, you don't, the other tasks were just waiting because they are virtual threads and your platform threads were busy. Yeah, 10 core. So we have runtime. So it is 10. Is it the same output for you guys? So what happens when if I want to actually give some time to other virtual threads, correct? So if how can I do that? I can say thread dot yield, right? I have thread dot yield. Okay, in this case, nothing is getting run. Why? We are eagerly yielding. So every task is saying yield, yield, I don't want to do, and nothing is getting run. So what we can do is, so only when around say every 1,000th time, I'm going to yield. You could see now it has started to hop because it is yielding at some point of time, right? Every 1,000th time it is trying to yield. This also you have to keep in mind while working with virtual thread because you would think your code is computation intensive and you are not expecting it to hop at all, right? But somewhere if you do some log.info and your logger is configured in a way to write in a file or something, that is again a IO operation. So unknowingly it might yield. So you have to be careful while deciding what to do, what to run on virtual threads. Okay. Are you guys seeing the same output? Yeah. So we have been seeing all the good parts, right? Now to the bad part. So what if I do, if I block inside a synchronized keyword, right? So this is just, this is same as your earlier IO code, correct? All you have changed is to add a synchronized keyword to your method, right? Now, sorry, right. It doesn't hop. Why? Because we have a concept called virtual thread pinning. Now, this virtual thread cannot be unmounted during blocking operation in two cases. It is pinned to carrier when your task is executing inside a synchronized block or method. Okay, that is one case. The other case is when it is executing a native method or a foreign function. Okay, any guesses why this is happening? Why the spinning is happening when, forget the synchronized keyword. Why is it when you are trying to block inside a native method, it is pinned to the carrier thread and you cannot unmount? Still right, but if you think about natively, even JVM code is binary code. It's going to, it is on the same level as your C code, correct? Your native function. So of course, yeah, due restrictions, there are some restrictions there, but that is not the problem.
Maintaining the states across threads.
Why would I maintain the state? Because my continuation has the programming state, right? I can mount and unmount. Every state is there. Sorry? That's what it, the whole idea is I'm going to unmount when it is hitting a network IO operation, right? Some blocking operation. But if I simply go inside the native, I'm not able to unmount. I won't. If I unmount, it will, there will be correctness problem. No, no, you forget IO. Let the native code do nothing, right? But if when the thread is running the native code, I cannot unmount. Sorry? No, no. It can identify the if you do some IO blocking, it can understand the data is back. It can do all those things. The problem is with the native code, you can refer. It has all the pointer operations, right? It can refer back to the stack variables. So you have options in JNI to say, hey, what is give me the address pointer of local variable I in this method. You can do that. What if I'm going to remove the stack and get back? So if I am getting back here, right? So the next time I mounted onto my PT2, all my variables address are going to change because the base address is different this time. And if I have my native code pointing to something else, I'm going to face the segmentation violation at the worst. That's why when there is a native code running in your task, I cannot unmount, even though you are not doing anything, or it can be unmounted. Okay, so this is the main reason. Understood, right? It has the reference to the address of the stack, so you cannot move it around. It's the same reason why it is pinned for the synchronized block also. The way the synchronized block is implemented is that it has to know, because synchronous block, right? It is as same as capturing the object monitor. So the information is stored in the object. Unfortunately, it is stored in the object header, like in which method it is actually you got the lock or something. So it is pointing towards your stack address. That's why you cannot remove, because if you remove again, unmounting stack address changed, so synchronized block will get the segmentation violation. Understood? So that's why. So right now already JEP was created to address the synchronization problem, because you could change the implementation of synchronized keyword, right? And it borrowed the work that they were doing for project Lilliput, where object header they were trying to reduce. So right now your thread is spinning, it is a problem, right? So how do I know whether my thread is pinned or not? So we have something. So everyone is aware of JFR, right? Java Flight Recorder. So it's a profiling tool that you have. If you can listen to that event, you can understand whether your code is actually pinning or not. Because we actually write very less enterprise application code, right? Most of it is third-party library. You have no clue whether they are going to make a IO call inside the synchronized block or not. Correct? So again, another deadlock scenario. I will address this if we have time. Okay. Right. So this is the pain point right now. Your thread is going to ping. That's a problem. So if you are writing a new code, you can work around this problem by using reentrant lock. Anyway, conceptually that is much more better than using synchronized keyword. So if you do that, there is no problem with reentrant lock. Okay, it's just the problem with the synchronized code. If you have the same experiment again, right? If you replace synchronized keyword with your reentrant lock, right, it will work fine. So already people have written JUnit extension for this, where an annotation like should not pin and should pin is written. So when you test your application with this thing, right, the annotation is implemented to listen for JFR event, and if it is actually at log with your expectation, it is going to throw error. That's how you can figure out whether something is pinned unintendedly or not. Okay. So as I said, there's already a JEP created and it's already delivered also. JDK 24, the virtual thread doesn't get pinned while executing a synchronized keyword. Okay. Right. So all the adoptions are right away. You can see Tomcat is already there. Jetty, somebody asked for, no, Netty, right? Sorry. Jetty is already there. Your connectors, right? Your SQL connectors. So that again, you don't want to make the IO call inside the synchronized block. So that was fixed in MySQL connector. So Quarkus, your application framework, that is fixed. This is Halidon NEMA, another microservice framework. They have moved to virtual thread. Spring is again, they have moved, right? So still we have time. I'll talk about this problem, right? So it pins. So what's the big deal, right? It is pinning. Your virtual thread is tied to your platform thread. Fine, right? Let my one platform thread has gone. Let other virtual threads wait. You could think like that. Problem is you might hit a unintended deadlock because of this. Okay, actually you have a war story here. Netflix actually wrote a similar article explaining this deadlock scenario. You could read about this. So what happens, say your virtual thread 1 is there. It is going to block while trying to fetch a data. So it is blocking. So what you do, you unmount, correct? And virtual thread actually, you have another virtual thread 2, which actually waits for virtual thread 1 to return that data. It is waiting for VT1 to come back. Okay, but your virtual thread 2 is actually using a synchronized block. Okay, which means that it is pinned to your platform thread. It cannot move. Okay, now virtual thread 1 is ready with the data. Typically what should happen is virtual thread 1 comes with the data, it should notify virtual thread 2, everything happens nicely. But because it is pinned, virtual thread 1 doesn't have anywhere to go. There it cannot run because your platform thread is already pinned. So this causes actually deadlock. It is very difficult to debug this because it's not your usual deadlock, right? Where you capture the locks in the reverse order, You just say JCMD thread.dump. It is nicely say this is the where it is logging. So this you have to debug really deep. So this is happening. Thankfully, 24 it won't happen, but 21 there have been questions like, will you backport it? Most like answer is no. So you have to wait till the next LTS, which is 25. Yeah, not the other way around. Because assume this, for simplicity's sake, assume only one platform thread is there. VT2 is not doing any work. Just to showcase, even if you have many things, this scenario can happen. Right. Issue because your platform, although VT2 is not doing anything, it is a good candidate for unmounting. We cannot unmount because of the synchronized power. Okay. Typically, when you write the code, you say, okay, VT2 is anyway going to wait. Let VT1 fetch and come back. It is going to notify VT2. Everything is good. But in this case, VT1 cannot notify because it doesn't have a platform thread to run. It is just the application logic where you could write such a logic, right? Nothing to do with the underlying.
Independent.
Right. So yeah, while you are writing the logic, you won't know this can happen. You would think VT2 is doing nothing, it's going to get unmounted, but it won't be unmounted. Okay, there is a re-entrant, since we have time for one demo. Okay, one last demo. Okay, with that we'll close. So this is doing the same. Okay, so you have a locking code. Okay, and I'm going to create one unpinned thread. Okay, this is going to capture the lock, and the rest of the pinning thread, I'm going to try to take the lock inside the synchronized block. Okay, if that is the case, it will never happen because all these guys are going to, so I created as many as the number of cores. So my unpinned guys are going to hog the platform threads, and my pinned guys are going to hog the platform threads, and it won't let the unpinned guy to unlock. Okay. So Java C. It's just waiting. Everyone is waiting for the lock, but the first guy, the unpinned guy, right? He has the lock, but when he wants to get it, there's no way he can mount himself to the platform thread. So if you, so if I don't do it inside the, so I have a variable here. If I don't do inside the synchronized block, right? Everything goes well. The unpinned guy is able to capture the lock is going to do. So we said that in 24 this is fixed, right? So this is getting locked. Okay, so where do I have it? So 25, sorry, 24 it's already fixed, right? In this is 21, you are seeing the pinning, but with 24 there's no pinning. Okay. Yeah. So most of this migration challenges you guys have asked us questions, so I think I have covered. Yeah. Thanks. The code is available in the GitHub. You could experiment and play around. Okay. Thank you, guys.